Hey everybody, today we're going to learn about clues to tell us whether or not the crust has changed due to being at a plate boundary. So this is called crustal deformation. So the word deformed. So if something is deformed, it means it has changed from its original condition. So if something looks really strange, you might say, wow, that looks deformed. Okay, so here is some deformed rock. We would call this an outcrop. You usually see this along a highway. If you ever drive upstate, you might see what's called a road cut, where they blast it into the side of a hill or a mountain so the highway can cut through. And if you look on the sides, you might see these rocks that are folded, tilted, or cracked, or we call faulted. That means the crust has gotten deformed. So what we're going to do in this lesson is attached to this video. This video is in a program called Edpuzzle. It'll stop with questions. So all the questions will be multiple choice. At the same time, you should open up the Google slideshow that matches this presentation and fill in the notes wherever they need to be filled in. So you're doing two assignments here. You're filling in the Google Notes as well as answering the questions that are embedded within the Edpuzzle. Okay. So what's the evidence of past crustal movement? Well, if the rock layers are deformed, we call this deformed rock strata. Strat rhymes with flat. So normally rocks should be flat or horizontal. So if they're not horizontal, so if the rocks aren't flat, like one layer of rock on top of another layer of rock and another one, we refer to this as normal or horizontal strata. So if the rocks are not flat or horizontal, that means something changed them. We would call that deformed rock strata. So there's three main kinds of deformed strata. One is due to faulting. So faults can displace rock strata. Rock layers can move up, they can move down, or they can move sideways relative to the fault. And all that depends on is the type of boundary that these rocks might have been at one time. So convergent and divergent boundaries can make the rocks move up or down, and transform boundaries will make the rocks move sideways relative to the crack, and the crack is called the fault. All right, the next thing is tilted. Sometimes the rocks are on an angle. So instead of being flat, something forced them upwards. So tilted strata were once horizontal layers of rock that are now tilted at an angle to the Earth's surface. And then the third is folded. So rock layers that have been bent. So everything in the green is in the slideshow that you have in your copy of Google Classroom. So you have to fill out the notes along with this video. All right. Next is a chart comparing or associating the type of boundary with the pressure that's caused and then the fault that would be formed. So let me move myself over here. So in a divergent boundary, divergent means to move apart. We spent a lot of time going over that. Stress is the force that's applied. So the force that's applied, or the stress that makes a divergent boundary move apart, is called a tensional or tension. You might just call it pulling force. This creates what's called a normal fault. And that's what a normal fault will look like. One block goes up, the other goes down. And if there's no erosion, if you look at the surface, the angle between the upward block and the downward block is an obtuse angle. And I'll show you how you can prove that a fault is a normal fault. All right. One of the other main boundaries is convergent. So while I'm bringing these notes up, you should be filling them in your copy. Convergent means to collide. which means the plates are getting pushed together. We call this a compressional force or a pushing force. And this creates really one kind of fault called a reverse fault. But if the reverse fault is really extreme, then we call it a thrust fault, because one block of rocks can get thrusted on top of the other. So there's a reverse fault. Okay, so in that one, you see that there's an overhanging cliff of rock at the top, and that will make an acute angle. So this picture, the top one, see that angle is obtuse, and this one's acute. And that's one way you could tell the difference in the kinds of faults, because both of them have an up-down motion. So the angle of the rocks relative to the fault line will give away the kind of boundary. All right, and the third boundary is transform. And transform is side-to-side motion. So it's as if the ground is getting ripped or sheared. Another word for scissors are shears. So this is a shearing force or tension, or a tearing. Okay, and the type of fault is known as a strike slip or a transform fault. And it's just sideways motion. And I showed you some images of the San Andreas fault already in this unit. All right, so normal faults. So normal faults are going to form the obtuse angle. So here's one image of a normal fault. And then another. And I'm going to bring up both images and show you what I mean by this obtuse angle, because you don't really see the surface on the picture on the left. And erosion could kind of wear away the ground and get rid of the obvious obtuse angle. So you shouldn't ever look at the surface really, because the surface gets changed by erosion. So if I bring up this image, okay, I'll show you what I mean by obtuse angle. So let's use the purple here. I'll make it a little wider. So this unit of rock right here is the same as that unit of rock. You will see that? The kind of the matching colors. So this chunk on the left got moved up. That's what that arrow is trying to show. And this one got moved down. And let me make my fault green here. And this is the fault line cutting through the rock layers. And this is what I mean by an obtuse angle, greater than 90. So that's what you look at. You look at the left side of the fault line and the right side of the fault line, and then you compare how much they got offset. So the block on the left got pushed up, the block on the right got pushed down, and along the fault line, it created that obtuse angle, which means this is a normal fault. So if you were hiking in a park and you came across an exposed cliff of rocks and you saw a huge fault, you now have enough knowledge to maybe know that fault might have been caused by a divergent boundary if the angle was obtuse. And if the angle was acute, it was caused by a convergent boundary. Let me show you one more. So this is the other picture that's attached to the slideshow. So let me use purple for the fault. This is the fault. Okay, and then they use red here to show the movement. So this red line is this like pale white cliff of rock on the left side, and here it is on the right side. So this section got thrown down on the left, and on the right it got thrown up. And it created this angle. You see that that angle is greater than 90. That means it's obtuse. That tells me that this is a normal fault, which means even though this area might not be at a plate boundary at all anymore, it was at one time at a divergent boundary, because only divergent boundaries could cause a normal fault. Okay, so let's continue on with the presentation. So this is just showing the breakage. Let me go back. Okay, sorry. All right, so you have this. It doesn't take long at all. It describes what happens in a normal fault, and one goes down and the other goes up, and it forms an obtuse angle. Okay, reverse or thrust faults, and that's, you look at an acute angle. So here's a reverse fault, and I would classify this one as more of a thrust fault. They're both reverse faults. Okay, you don't have to say thrust fault. A thrust fault is just an extreme reverse fault. Let me show you this in a drawing. So I'll use this purple again for my fault line. So here's my fault. You can kind of see that tan rock, kind of rust colored, reddish tan here, and then here. So this chunk got moved on the left of the fault, got moved up, and this one on the right of the fault got moved down. And now if you look at the angle created by the fault line, it's acute. See how this is less than 90? So even though this might be an area like the other faults that could be far from a plate boundary today, so maybe this was taken in upstate New York and they're nowhere near a plate boundary today, that means this fault maybe was at one time at a convergent boundary, because that's a reverse fault. Okay, and then the other image, see, it's more extreme. You have, you got a little more bold. You have your fault line here, and above that fault line, if you look at that darker red, let me use red, sorry. Doesn't want to change the red. Okay. That darker red right here, see this section? Kind of got thrown right above the same rock here. So it got thrusted above it, and that's why we call it a thrust fault. And then if you look at that angle, this angle right here, see that? It's an acute angle. So once I do that, I find the angle, and an acute angle tells me it's a reverse fault, and that lets me know this was at one time at a convergent boundary. Okay, so let's present it again. Okay, so here, pressure, compression forces one block up over the other, right, causing an acute angle. All right, transform boundaries form transform faults. Another name for them is strike slip, and it can either be a left lateral, which means the fault moves the land to the left laterally, which means sideways, or a right lateral. So first we're going to look at a left lateral fault, and I have an image of this as well. So here is a fault. See how there's no up or down motion? So this means you know it's a transform fault, but how can you tell if it's left lateral or right lateral? Okay, well, this is the fault line. Okay. And this green line I'm drawing should have been continuous with that green line. So that means this fault is left lateral, because on the top here above that purple line, everything got shifted to the left. But if I was standing here looking across this way, that also got shifted to the left. I knew I drew the bottom arrow to the right, and you got to imagine if you're standing at X, that actually moved left relative to you. So we call this a left lateral fault. And while I'm on this page, I'll bring up a right lateral fault. So this is a right lateral fault. So here's my fault line. Pretty amazing. This whole field was once together. Right? Look at that. And it's pretty obvious that this moved to the right relative to that fault line. But, if you're standing here looking across, this actually moved, the other side moved to your right. So if you're at X looking towards Y, Y would also move to your right. So this is a right lateral fault, and that's actually what we have going on in California, a right lateral fault. Okay. So here's your left lateral, and here's your right lateral. So these are all in the slideshow you have in your Google Classroom if you want to go back and look at these images. And the way I drew on them is I just inserted it into Google Keep, which I already showed you how to do. So you can separate each of these images and draw exactly what I was drawing if you want to take notes in even greater detail. All right, tilted rock. The rock's just slanted up on a tilt. It's pretty simple. It's not flat, it's tilted. Usually the way this happens is you had flat-lying rock, and usually what's called an igneous intrusion. So that means igneous rocks from below, like a huge magma chamber, came up through the ground and punched the land up, see, making it tilt. So it was flat, and then something from below came and forced it up on a tilt. So obviously this isn't flat. It once was. Something caused it to change. So it's evidence of crustal movement. All right, folding. So if you have something and you push it together, it folds. Pretty simple. So this can only happen at a convergent boundary because you need compression. You need to push things together. See, I have a piece of paper. If I want to make it fold, I got to push it together. And I get an upward fold and a downward fold. So only can occur at a convergent boundary because you must have compression to make rocks fold. Okay, the pressure and the heat that's applied with friction causes the rocks to be more malleable or flexible. And so even though you would just think the rock should break, and that's your fault, sometimes the heat and pressure allows them to be a little more flexible, and instead of cracking, they fold. So here's some really deformed land. Look at that. So you have an upward fold like that, or it makes like an arch, and then like a U. And we call the one that makes the arch an anticline. And it looks like it's frowning. So the fold that looks like a frown, we call that an anticline. And the one that looks like a smile, which is the bottom of the fold, or the trough if you think of it as a wave. So if you think of the fold as a wave, the top of the wave is the crest. That's your anticline. And if you remember, the bottom of the wave is a trough. We call it a syncline. I always remember the syncline smiles. S with S. So if it looks like a smiley face, that was a horrible smile I just made. Okay, we call that a syncline. So here's an anticline. See, it's frowning, or it's your crest of the fold. I'll bring up this image. Might be that one. Nope, it's the next one. Okay. So right here. See? It's frowning. That's a horrible face. Man, I'm a horrible artist. All right. Let's draw it here instead. So here, see this fold. So you know if this was a face, it has a frown. All right, so if it makes a frown, anticline. Anti sounds like upset anyway, right? Anti anything, you're not going to be happy. Okay, and then if it smiles, like this one, nice broad, look at that broad smile there. Okay, see how happy he is? All right, so if he smiles, it's called a syncline. Next time you drive upstate to a mountainous area, and not actually the Catskills, further north, like the Adirondacks, or definitely if you go out west into mountain ranges, and you go into these road cuts, you'll start noticing that the rocks aren't flat. They happen to be flat in the Catskills, so we don't consider the Catskills to be true mountains. They were mislabeled when they were first discovered. All right. So that's your anticline. And then you have your syncline, which smiles. I like this little demo. Someone made sand layers in a tray. Just listen.
When continents collide. In this experiment, we see two continents separated by an ocean. Now watch what happens as the plates converge. As one plate subducts or dives beneath the other, the ocean basin closes. The continental crust, which is lighter than oceanic crust, cannot be subducted. Instead, as the continents collide, the crust thickens and is forced up.
See how you get that crumple zone?
Note how the sand is folded and faulted. We see similar structures in the rocks in mountains. One important factor not accounted for in this model is erosion. Erosion exposes the deformed rocks that were once deeply buried in the mountain belt.
Look at those folds.
The green sand represents the rocks of the ocean basin. Note that it's been trapped between the two continents, marking their original boundary. These too we see in mountain belts. It's very difficult to understand the deep structure of a mountain belt by direct observation. The sand model allows us to compress time and space and simulates the internal structure of mountains.
Okay, so I think that model was very good. They actually poured all these different color sands in this huge kind of, I guess, water table in a way. And then they compressed it, making it fold, really demonstrating how mountains can form and why they're folded. Okay, that was all of today's lesson on crustal deformation. So I hope you filled in the notes. Remember to click turn in, as well as you should have done all the questions that were embedded within the Edpuzzle, which this video is attached to. All right. Have a great day. Once again, if you have questions, email me, or I'll see you at our Google Meets and I'll answer the questions there. Bye-bye.